Okay, so let's begin with arc length and speed. So if we have a curve, so if we are in three-dimensional space and we have a curve, we would like to be able to find the length from some point from some point A on the curve parameterized. So this would be t is equal to A to some other point on the curve, t is equal to b, where again this curve is r of t is equal to x of t, y of t, z of t. So we would like to be able to find this arc length. So one way to try to think about it is by considering this thing over here. Let's say it's delta y, and then you will have something in the x direction, which would be delta x, and then something in the z direction, which would be delta z. What I mean over here is if you look at a small change over here, let's call this change ds. So that's a small change on the length of your curve. Well, that, your ds, is going to be equal to the square root of dx squared, the length in the x direction, the amount that we're changing in the x direction, plus dy squared plus dz squared. So we can say that the length so this is our length, our arc length. It's the adding up all the small changes from a to b of ds. Well, that's going to be equal to the integral from a to b of the square root of a dx squared plus dy squared plus dz squared. But the problem is these bounds are not really well understood. We would like to put this in terms of t. So this would be the same as ab, and then we would have the square root of dx over dt. So what I'm going to end up doing is I'm going to end up putting a dt here over dt, which is fine. And then I'm just going to leave that dt, and I'm going to move this dt inside. So that would go in here. It goes in the square root, so it gets a squared plus dy over dt squared plus dz over dt squared. And that's going to be my length. So we can say in general that the length is going to be equal to the integral from ab of the square root of rx prime of t squared plus y prime of t squared plus z prime of t squared. And this actually is also equal to the integral from a to b of the magnitude of r prime of t dt. Right, the magnitude of r prime of t will give us this, the square root of, and then we would get our dt over there. So going back to the text, yeah, if we have a curve r of t, then our s, our arc length, is going to be equal to the integral from a to b of the magnitude of r prime of t, or what we wrote out. So now they ask us to find the arc length of the helix given by cosine 3t, sine 3t, and 3t. So r of t is equal to cosine of 3t, sine of 3t, and 3t. So this is a helix. So second. Let's start a new one. Are there any questions about this so far? Okay. So R of t was equal to cosine of 3t, sine of 3t, and 3t. So this is a helix. If your z coordinate is 0, then this over here, we can say, okay, this is x of t, and this over here is y of t. So x of t squared plus y of t squared, that's going to be equal to cosine squared of 3t plus sine squared of 3t. We just take it from here. And this over here is equal to 1, which gives the restriction x squared plus y squared is equal to 1, which is a circle. So if you don't look at the z direction, we get a circle. But if you include the z direction, then you get a helix. Okay, and we want to find the the arc length from 0 to 2 pi. So 0 is less than or equal to t is less than or equal to 2 pi. So the way to do this is just by looking at, oh, 1 second. The way to do this is by looking at the integral from 0 to 2 pi of the magnitude of r prime of t dt. So this would be the integral from 0 to 2 pi. And then we would have the square root. And so again, so r of t was equal to cosine 3t sine 3t and 3t. So then we would get over here negative, so let me do r prime of t is going to be negative 3 sine of 3t cosine, so 3 cosine of 3t and 3. So then over here we would get this thing squared, so that would be 9. I'm going to take out the 3 and the 3 from there, and this squared are going to be 1, but I'm going to write it out. So that's cosine squared of 3t plus sine squared of 3t plus 9. And so then this is going to be, so this is 1. So this is the integral from 0 to 2 pi of the square root of 18, which is going to be square root of 18 times 2 pi. Yep. Okay. So any questions about that? Is it clear?
It's clear.
It's
All right.
clear. Could you just go back so that I can finish copying it down, please?
Yeah. Okay.
Thank you.
Okay, so now we can try to figure out, so what would ds over dt be? So ds over dt. What does this mean? Well, it means the change along the x as you change t, which would be your speed. This would be your speed. And by the fundamental theorem of calculus, so we can first write this equation over here. We can say, let's take s of t in general to be equal to the integral from a to t of the magnitude of r prime of t dt. And as you put different t's over here, you'll get different arc lengths starting from a. Now then, ds over dt, for such a thing, ds over dt, by the fundamental theorem of calculus, the t just goes in. That would be the magnitude of r prime of t. So what this means is, if you have a curve, and you want to find the speed at some point on the curve. So you want to find how quickly the particle is moving exactly at this point. Well, first we said we could look at the tangent vector, and that was r prime of t. But the tangent vector doesn't really give you the speed. It just tells you the direction in which this particle would be moving if I cut the curve right here. If I let the particle off the curve, it would start going in that direction. But in what speed? And the answer to that is that you take the magnitude of this, and that will give you the speed. Okay, at the point t. So whatever point. So this is the point t. Okay, and that is this formula over here. ds over dt is the magnitude of r prime. So let's do an example. So let's say r of t is t cubed. So r of t is equal to t cubed negative e to the t and 4t. Negative e to the t and 4t. And we want to find the speed. Yeah, at t equal to 2. Okay, so t. Okay, so again, we're looking for the magnitude of r prime of t at 2, or really the magnitude of r prime at 2. So first, r prime of t is going to be equal to 3t squared negative e to the t and 4. So the magnitude of r prime of t is going to be equal to, and honestly, let's just plug in t actually at this point. So let's just look at the, so r prime of 2 is going to be equal to 12 negative e to the 2 and 4. So the magnitude of r prime of 2 is going to be equal to the square root of 12 squared plus e to the 2 squared plus 4 squared. That's going to be our speed. And they tell us that that is, so that's that, and that's equal to 14.6 feet per second. So that's the speed of the particle at that point. Okay. So now different curves can be parameterized differently. We talked about this. So if this is my x and this is my y, a simple curve over here would be y is equal to x squared. And this is a curve. It's not parameterized. So there's no t. You don't have an rt over here, 2 coordinates. But we can parameterize this curve by setting x is equal to t. And so then r of t will be equal to t comma t squared. And this is my x, and this is my y. So my y, which is equal to t squared, which is equal to x squared. And now I parameter, when t is 0, I'm here. This is t is equal to 0, and t is 1 would be here, t negative 1 would be here, and so on. But you can parameterize this curve in a different way too. You can now take t to, let's say, be equal to u, I don't know, cubed. And then we will get r of t is equal to u cubed, u to the 6th, and so on. So different curves can be parameterized differently. And that's the next topic. So first let me explain what I just said. So if we can have 2 parameterizations of the given curve. So the parameterizations are not unique. So we can have t squared and u to the 6th, and they both parameterize the parabola y is equal to x squared. Okay, and so one second. So in any time you have a parameterization, you can get a new parameterization doing what we just did by substituting some function in. Okay, so, and here is an example. So if you have a curve and it's parameterized like this, we want a given parameterization and where now t is going to be e to the u. So you just plug it in. I'm not going to go through this, but you just plug it in, e to the u squared, and the 2 comes down, and then e to the eu because there's a t in eu. Okay. So now they would like to be able, so is there a way to if you have any curve, is there a way to reparameterize it so that the derivative, the speed along the curve is always equal to 1? That's the next question. So if I have some curve, and so here's my curve, and it's parameterized, can I reparameterize it, find a new parameter, so that from my new parameter, let's call it R3 prime of t, the magnitude of this thing always equals to 1. Okay, and the way to do it is fairly simple. I'm not going to go through the steps, although they are intuitive. So obviously the first step is you want to find the actual arc length for the situation that we're in, and that will, so you go from 0 to t, and then we would like to be able to find the inverse of this s. So you want this g, you want to get the inverse, and that would tell you what we're looking for, and then we just plug it in, and that's that. So let's do an example. So they're giving us r of t is equal to cosine 4t, sine 4t, and 3t. So r of t is equal to cosine of 3t, sine of 3t, and 3t. Oh wait, was it 4? Oh, 4, 4, okay, and 3t. Okay. So again, the first thing that we would like to do is, for any t, we would like to figure out what the current arc length is. So we want to take the integral from a to t, and we're going to take this to be our s. So we want to take the integral from a to t of this thing, of the magnitude of r prime of t dt. So that's going to be the integral from, actually 0, let's go from 0 to t of, okay, so now we're going to have, so the derivative and then squared. So this is going to be the square root of, and I'm going to take out the 4 and squared at once. So that would be 16 times, and then the derivative of this would be negative sine squared, and this would be cosine squared. So it would be 1 as usual. Plus the derivative of this is going to be 3 squared would be 9. And so this whole thing is going to end up being 5t. So far, is it clear?
Yes, it's clear so far.
So now s is equal to 5t. So I can say, in order to reparameterize this, t should be equal to s over 5. Just find the inverse. And now we plug it in. So r of s over 5 is going to be equal to cosine of 4s over 5 sine of 4s over 5 and 3 s over 5. Okay, so now let's see if this worked. So I'm just going to do it like this. So we want to see if the magnitude of this. So I'm going to. So is the So let's Let me say that this now is equal to R2 of s, or R of s. Sorry, this will be equal to R of s. So now is R of s the derivative, so is r prime of s, we take the magnitude, is this always equal to 1? That's our question. So in order to, so this would be the, so the magnitude of r prime of s is equal to the square root of, okay, and then you take the derivative of the cosine, so you get 4 over 5, and then that would be negative sine squared, and this would be this, and I would take the 4 over 5 out there too, so you would get a 1 over here, and this would be squared, plus, and then the derivative of this would be 3 over 5 squared, and then this will be the square root of 16 over 25 plus 9 over 25, which would be the square root of 25 over 25, which would be equal to 1. Okay? Okay. So that's what they ended up doing, and they got the same thing. So in summary, in order to find the arc length from A to B, we're going to use this formula. And in order to find the speed, we will take the magnitude of r prime. And we can always reparameterize the curve so that the speed is always 1. And we do this by finding the arc length function from 0 to t. So that would be this, from 0 to t of this, and then we solve for t. So we take g inverse, we solve for t, and that will give us our solution. Okay, so are there any questions about this? Or can I move on to curvature?
No questions.
Okay, so let's continue with curvature. So when you have curves, you might want to find the curvature of these curves, how curvy they are. So a line would not have any curvature. Maybe this would have some curvature, a circle would have some curvature, and so on. So the first thing that they want us to know is what the unit tangent vector is. And pretty simple, we know what the tangent vector is, it's r prime. So now you take r prime over the magnitude and you get the unit tangent vector. And they do an example for us, but I don't think that that's necessary. And so then they tell us that the curvature is going to be the change in that unit vector over the change in s, which would basically mean, so again, if we are in three-dimensional space and we have a curve, then we now know how to find the unit tangent vector to this curve. This is t of t. And we said that that was equal to r prime of t over the magnitude. Now, the curvature, kappa, is equal to the magnitude of the change of the unit tangent vector over the change in ds, which means as I vary ds, as I move, so ds is the small lengths over here, as I move along the curve, as I vary my ds, so this would be a ds, the unit tangent vector also changes. So over here, maybe I had that tangent vector, and over here, maybe I had that, I don't know. They actually look pretty similar, but whatever. So as you move them, your unit tangent vector might move a little. And that would give, and so if you're a line, then this would be 0. Why does this keep happening? 1 second. So if you're on a line, then your unit tangent vectors are always the same. And so the kappa of s would be equal to 0. But if, let's say, you're in a circle, your tangent vector is always changing, your unit tangent vectors. And so you might have some curvature. Okay, any questions about this so far? Okay. So in the next example, they show you how to find a curvature of a circle. But I actually you don't need to know how to use this formula in order to find the curvature. And it can get a little technical. It's generally better to use this formula, because the other formula you need to take an integral sometimes. Anyway. So this formula will always get you to the curvature. It's the magnitude of r prime t, r prime of t cross r double prime of t over the magnitude of r of t prime cubed. And this would also give you the curvature. So let's do an example. So here's an example. Calculate the curvature of the twisted cubic, which is this, then plot the graph. So we're not going to plot the graph, but so now my r of t is equal to t squared and t cubed. T squared and t cubed. So my curvature is going to be equal to, well, we said it's the magnitude of r prime of t cross r double prime of t over the magnitude of r prime of t cubed. So r prime of t is going to be equal to 1, 2t, and 3t squared. And r double prime of t is going to be equal to 0, 2, and 6t. So then r prime of t cross r double prime of t, that's going to be the determinant of the matrix I, J, K, 1, 2t, 3t squared, 0, 2, 6t. And this is equal to, okay, I times, and then this over here is going to be 12t squared minus 6t squared minus j times 6t plus k times 2, which is equal to 6t squared negative 6t and 2. Okay, do they want the curvature at a given point? 1 second. No, okay, fine. So then, the magnitude of this, because we need the magnitude of this entire thing. So let me just write down what would be here. It would be 6t squared, so the square root of 6t squared plus 6t squared plus 4 over, and then the magnitude of this cubed is going to be the square root of 1 squared plus 2t squared plus 3t squared squared, all this cubed. And that would be the answer. Any questions about this? Okay. So the next thing is that they give us the formula of the curvature of a plane, but you don't actually need to know this formula. You can just use the above formula because it's a generalization. So this is just for a curve in a plane, for a curve with only an x and a y without a z, and that would be the formula, but you don't actually have to memorize that. So I'm gonna kind of skip this part. And then this over here is the curvature of a graph. So again, now you have x and f of x. Again, slightly different formula, but it comes from the above formula, so you don't actually need to memorize them. You can, again, if anytime you're given a graph, you can turn it into a parametric equation by saying r of t is going to be equal to t and f of t. And then you can put this in 3 dimensions by saying, okay, that would be t, f of t, and 0, and then using the formula that we just had, magnitude of r prime of t cross up r double prime of t over the magnitude of r prime of t cubed. So you don't actually have to memorize this formula either or know how to use it. Okay, so now we're going to continue with the normal vector. So if you have a curve, so again, we are in 3 dimensions, we know how to find the unit tangent vector. Now we would like to be able to find the curve normal to the vector normal to the curve. So that would be orthogonal to the curve. So this over here, n of t, would actually be t prime of t over the magnitude of t prime of t. Okay, and that will be our normal vector. So before I continue, actually, I wanted to mention the type of questions, at least one question that might appear on the quiz on Friday. And if you have any more questions about this, just let me know. But let's say you have 2 curves. So here's one curve and here's another curve. And they intersect at some point. So this is a point t is equal to, let's say, I don't know, 3. And let's say I want to know the angle of these curves where they intersect. Does anyone have an idea of how I can do that? Anyone? Okay, so what you can do is you can find the tangent vector to this curve, and you can find the tangent vector to this curve at that point. So this would be, so let's say this is r1 of t, and this over here is r2 of t. So you can find r prime of 3, r1 prime of 3, and you can find r2 prime of 3. And those would be the 2 tangent vectors at these. And now, so now you have 2 vectors, and finding the angle is the same thing as finding the angle between these 2 vectors. So the angle is going to be equal to cosine inverse of r1 prime at 3 dotted with r2 prime at 3 over the magnitude of r1 prime 3 magnitude of R2 prime 3. Yeah, is this clear?
Yes, it is.
Okay. So this is the type of question that can appear on the quiz. It involves new stuff that we just learned, like derivatives of curves and stuff, but also old things like how to use the dot product in order to find angles. So, okay. So that was the normal vector. And so here's our normal vector. Our normal vector is t prime over the magnitude of t prime. So going back, here is our normal vector. Oh, and it looks like the curve got erased. Let me actually go to new whiteboard. Okay. And they find the normal vector to a helix. It's so here's a helix that we looked at before. You take the derivative, and you get that this is the square root of 5, because again, sine squared cosine squared is equal to 1. So you get that your unit tangent vector of this helix is 1 over the square root of 5 of this thing, of the tangent vector. So that's what we saw before. And so then this would be the unit, so this would be the unit tangent vector. And this is the derivative of the unit tangent vector, which we need for, in order to figure out the normal vector, you need to take the derivative of the unit tangent vector. So here's the derivative, and here is the magnitude of that derivative. And you can get your normal vector by putting one and dividing it by the other. Okay. Any questions? Okay, so, and then the last vector, so over here we just found two vectors, this vector and this vector. Now we can take their cross product, let's say t cross n, and that would give us a third vector orthogonal to both of them. So now you would have three different vectors, and they call this the binormal vector. So our B, the binormal vector, is very simply t cross n. So it's orthogonal to both. So now you have like a little frame. You would have this vector, your normal vector, your unit tangent vector, and your binormal vector. And so here it is, normal, binormal, unit tangent. And they give the same example. So we computed the unit, we computed the normal. They ask us to compute the binormal. Well, that again, just you need to take the cross product, and they do, and that's what they get. Okay, and I'm going to skip the section with oscillating plane and circle. So that will be the end of this section. So in summary, in order to define the unit tangent vector, we take the tangent vector over its magnitude. The curvature is then going to be that tangent unit vector over ds, the magnitude of that thing. That will tell you how quickly the unit vector is changing as you move along your curve. And we found an equation for the curvature. And okay, now these equations we said are actually not that important. We're not going to talk that much about it because you can always use that equation. And then we talked about the normal vector, which is you take the derivative of the unit tangent vector, divide by its magnitude, and that would give you the unit normal vector. And it's orthogonal to your curve. And then we said we can find the binormal vector by taking the cross product between the two. And okay. So next class, we are going to continue with, let me see, with the space, with movement. Second, yeah, motion in space. And then we're going to review next Tuesday for this exam. On Friday, you're going to have a quiz. Again, it's going to be up to everything, including arc length and speed and curvature. So all the things we just covered, but also how to take the derivative of a curve. I mean, how to find the tangent vector of a curve. Different quadratic surfaces might appear. And again, the other stuff, the things that we did before also might appear on the quiz, but in like a new format. But you still have to know, obviously, how to take the cross product, take the dot product, and stuff like that. And that's basically it for today. So are there any questions? Quiz, the test, the homeworks, anything?
Hey, real quick, will there be any practice on like what we just learned?
Before the quiz, you mean? To
Yeah.
some degree, I'm considering the quiz to be a review for the exam, but I'm not going to review for the quiz. No. So so just try to do the homeworks. That should help you review for the quiz. And yeah, but I'm not going to. Maybe next class, if I have time. I actually probably will end up having some time. So towards the end of the class, I'll try to review the material, but I'm not promising anything.
Okay.
Will we have the same amount of time for the quiz as we did last time?
Yeah, 3 hours, and it will be 5 questions. So it should not be hard, and it's just like just to prepare you for the exam. It's basically it. Okay. Any other questions?
Hey, will the exam coming up be like the exam 1 that we took? Like same format?
Yeah.
Okay.
All right. Okay. Okay. Have a nice day. Bye.